So today we're going to be going over set theory. So set theory is all about understanding and working with sets, which are simply just collections of distinct objects. And these objects can be anything from numbers to letters or even other sets. So for example, if we want to have a set of natural numbers less than 5, we can denote it by curly brackets, and then in our set we could have 1, 2, 3, and 4. As well as if we had a set which contains no elements, we can either write it as the null, which is a 0 with a line through it, or just an open and closed curly bracket with nothing in between it. So now what we have is, using these sets, something that we could use now is Venn diagrams. So for example, if we had our A and we had our A equaling to 2 and 4, and we had our B equaling to 1 and 4. What our sets are with working with Venn diagrams is, if we drew our two circles and we had our interlap and we said this was our side A and this was our side B, all our sets are saying is that everything in our set of A that is just an A stays together, and everything that is in our set B stays together, and then the things that match go in the middle here. So the way the Venn diagram works is we will have our two separate sides, our left side and our right side, labeled as our A and B, and what those are is just the elements that are in our A without the ones that are matching in A and B. So now we have another thing that involves Venn diagram, that being subsets. So if we had our A equaling to 1 and 2, and our B equaling to 1, 2, 3, and 4, and we want to see if A is going to be a subset of B. What this means is A will be a subset of B if all the elements of A are in B. So we notice that A has 1 and 2, and so does B. So we could say that A is in fact a subset of B because all the elements of A are in B. However, we cannot say that B is a subset of A because even though they both share 1 and 2, B has 3 and 4, which aren't in A. So we can't say that that fails. But if we were to draw this with a Venn diagram, we want to have our square on the outside, and this is going to be known as our space. And when we have our space, the only time that would have numbers out in our rectangle is when the numbers aren't inside of our A or B. So in order to draw our A and B here is going to be a little bit different than our Venn diagram, because as we notice, our B is going to be our 1, 2, 3, and 4. So this means that our A has to be inside of B, because A is a subset of B. And this will be our 1 and 2, and just in our B is going to be our 3 and 4. However, if we said in our set we also just randomly had the number 5, that is when it would be outside of our A and B, and that would be just regularly in our space. So next up is we want to check our AND. So what this is going to be is when we have this is going to be our intersection of A and B. Or to make it easier to remember, it's our, if we write it like this, it's our N, so AND, meaning that it's in both A and B. So if we had A equaling to 1, 2, and 3, and our B equaling to 3, 4, 5, the way that we check for our intersection is by seeing if we have any matching terms. So we see that both A and B have the number 3. So our A intersection B is going to be equal to the number 3. So again, if we were to draw our Venn diagram to match this, and we had our A circle and our B circle, our intersection is going to be whatever is in this small sliver in the middle. So we see that A has 1 and 2 just by itself, so we'll write 1 and 2 there, and B has 3 and 4 by itself, so we'll have 4 and 5 by itself. And then the intersection, or this little sliver in the middle, is going to be the number 3. And when we're writing what the intersection is, we're going to write what numbers are in the set. So for example, if we had our A equaling to 1, 2, 3, and 4, and we kept the B the same as just 3, 4, and 5, the intersection of our new A and B would be equal to both 3 and 4. So our next topic is the union of sets. So this works close by with our and. So with our and, we know that it looks like this, but now we want our union. So our union is going to instead look just like the upside down, and it's going to be A union B. And what this means is it's going to be A or B. So when we're checking for the union of a set, it's going to be anything in A or B. So the difference is, if you remember, when we had our A equaling to 1, 2, and 3, and our B equaling to 3, 4, 5, we checked what was the same. It was in A and B, which was our intersection, which is equal to 3. However, for this one, we want if it's in either A or B. So as we can see, our A or B is going to be equal to absolutely anything in all of them. So first we could write our A as 1, 2, 3 because it is in A, or B. So we don't need to write the 3 a second time, but then we can just write 4 and 5. So the way this one looks on a Venn diagram is if we had our A and we had our B, we're looking for anything in this entire Venn diagram rather than just the middle. So because we have our 1, 2 here, and we have the 4, 5 here, and we have our 3, we're just looking for all of it. So that's what gives us our 1, 2, 3, 4, and 5. And our final topic is the complement of a set. So what the complement of a set means is we're going to want anything that is not in our set. So for example, if we had A equaling to 1 and 2, and we said that our universal set, which just means any number that we're allowed to use, is equal to 1, 2, 3, 4, and 5. When we want to find our A complement, which is going to be A with a little mark on top, it's going to just be any numbers that are in our total set that isn't in our regular set of A. So for example, we have our 1, 2, and 1, 2, 3, 4, 5. So to get our A complement, we just ignore the 1 and 2 and just write 3, 4, and 5. And what this will look like, again, on a graph, is if we had our A here, of 1 and 2, and this was our sample space. Our A complement is just going to be anything that's outside of our A. So it's going to be anything on this outside part. So this will be R3, 4, and 5.